Hi everyone, thanks for joining in for this presentation. The title of this presentation is Some Exploration of Path Dependence in Contact Analysis. My name is Gaurav Chowda and I work with my advisor Dr. Daniel J. Siegelman. I am a fourth year PhD student in Department of Mechanical Engineering at Michigan State University. So first, the brief overview. We will first start with a brief introduction, then discuss about contact algorithm, then few results, explain path dependence, and then finally, I will conclude the presentation. So the motivation of this study is to study the interfacial contact mechanics to understand the nonlinearity in mechanical joints. Interfaces of these joints are inaccessible during the dynamic loading, so we require a numerical methods to understand their behavior. And the numerical method require a very fine discretization of contact surface and also require a good contact algorithm. Most of the contact algorithms are adequate with Coulomb friction model, but Coulomb friction model is not adequate to explain the nonlinearity of joints behavior. So we need a test bed with very fine discretization and also have a robust contact algorithm so we can implement multiple friction models. So we can predict accurately the quasi-static stick-slip region during the dynamic loading, and also observe the dissipation behavior which is happening in the interfaces. Satellites and the turbines are the very important example where the joint dissipation and stiffness non-linearity is very important and create critical issues in these things. Below is the example of Brake-Roisby, which is one of the simple joint model which people use for the experiments. So before we go further, we talk about the contact taxonomy. For the 2D contact analysis, we can have each discrete node can have four contact status. Each status is each status will have equality and inequality constraint. So four status are first like a stick, left slip, right slip, and non-contact. And each status will have its own two equality constraint and one or two inequality constraint. So for contact and stick status, we will have a lateral velocity to be 0, and the two surfaces are in contact. Our traction force will be less than friction force or break-free force, and there will be a normal pressure because the nodes are in contact. Again, when the second status, contact and slip right, we will have traction equal to the break-free friction force. The node will be in contact, but the node will allow to slip in one of the direction. In the contact and the slip left, the direction of the traction will change. Also, the direction of slip will change. Finally, for the nodes which is not in contact, we will have zero pressure and zero traction, and there will be a gap between two surfaces. So there are many algorithms in the literature, and there are a lot of work on the contact algorithms. Here we are using one of the conventional algorithm, which is developed by Ann and Dr. James Barber. These conventional algorithms have some instability, and the algorithm shows some non-convergence near to if we are using a cyclic shear loading or very high elastic coupling. And also if we are changing multiple node status in a load step, it also results in an erratic solution. So we modify we modify and did some modification with the conventional algorithm to make it more robust. So in the modification, we allowed only one node change status at a time, and also at the start of each load step, we make sure that all the node we make them a stick status, and then allowed each node at a time, starting with the worst offender. Still, the conventional contact algorithm cannot guarantee us to provide an admissible solution, even with admissible converged solution, due to not satisfying all the equality and inequality constraint during the loading. So we require a more robust and rigorous contact algorithm. So we developed a contact algorithm method of first violation, which we can understand like by observing if there is a load increase from L to L plus delta L, and if there is no change in the node status. So the problem will be linear in this region. So we can say if there is a linear increase in load results in a linear increase in contact parameters. So contact parameters such as normal pressure, lateral traction, lateral displacement, and normal displacement. So instead of choosing a load step and then resolving multiple node status violation inequalities over that load step, we can find that particular load step that will cause the first nodal status violation in inequalities. So for that one constant type, the load step can be solved by a linear analysis. So the central idea of this algorithm is find any highest load step that does not cause a violation, or equivalently find the lowest load step that cause a violation of a node status. So that load step we can call is a first violation load step, and at that particular load step, all constants are satisfied. Equality and inequality constants are satisfied at the beginning of the load step, and also at the end of the load step. And because the problem is linear, so it is also satisfied during the loading. So to have a contact problem, we used this 2D contact problem where rigid cylinder is pressing on an elastic half plane, and half plane is discretized in very small segments. We have analytical expressions. Using that, we can create a compliance matrix for this contact problem. So here is a complex problem with very high coefficient of friction and full elastic coupling for Coulomb friction, where coefficient of Coulomb friction is 3. So we can see for this problem, the conventional algorithm shows instability, and it shows instability near to the edges, and also show hash behavior in the stick region. On the other hand, the method of first violation provided a stable result and smooth solution with a proper distinction between stick and slip region. But we like to understand the dynamic, like nonlinear behavior of joints. So we implemented other friction models. So here we implemented the 2-parameter Coulomb friction with Goodman decoupling approximation, where the coefficient of static coefficient of friction is 0.7 and kinetic coefficient of friction is 0.49. So first we press the cylinder normally, and we find that both normal pressure and the lateral pressures are in line with each other. But as soon as we applied a lateral pressing on the lateral load on this rigid indenter, we find the conventional algorithm start to show instability, and we can see the hash behavior near to the contact edges. And in the slip region, you can see there is a zigzag in the with the lateral traction we calculated from the conventional algorithm, whereas the method of first violation provided a smooth solution with a proper separation between stick region and the slip region, and provided a proper solution here. So in conclusion, the method of first violation is extremely robust. The algorithm satisfies all equality and inequality constraints at the start of the loading, at the end of the loading, and during the loading. Also, the method of first violation algorithm is fairly easy to implement with other friction models. So for the future work, the algorithm can be useful to get insight in nonlinear joint dynamics. And we intend to investigate the algorithm further for the non-uniqueness and non-existence of the solution along the clubbing conditions. Thank you for listening, and now I can have your questions.